All right, in this module, we're going to introduce everyone to the notion of hydrostatics. And in particular, we'll focus on chapter 2, which talks about the pressure distribution within the fluid. And the fluid can be a liquid or a gas, as we will see as we progress through this chapter. Here are situations in which hydrostatics comes in handy. So the fluid is either at rest or the fluid is such that there are no gradients of velocity anywhere in the fluid, right? So in other words, if I'm looking at a fluid in a container, for instance, and so let's say there's fluid in this container. If I take a point here, and if I take a point here, and if I, let's say, take the x component of velocity, assuming this is the x direction, the x component of velocity, at these two locations, they could have velocities at those two locations, except that the difference in velocity, that is the derivative with respect to x of this x component of velocity, is 0, right? And likewise, the derivative with respect to y and the derivative with respect to z of all components of velocity are 0. In other words, there are no velocity gradients that exist anywhere within the fluid, right? So those are the situations under which we can apply the principles of hydrostatics. And if we don't have these velocity gradients, if you recall in chapter 1, where we introduced the notion of viscosity with an upper plate moving and a lower plate held stationary, we set up tangential stresses which created motion of the fluid instantly, right? So the advantage now in hydrostatics is only surface forces that can exist are only these normal forces or normal stresses. The tangential shear stresses that we talked about in introducing viscosity are not allowed, right? So it simplifies the problem. So the role of viscosity is not relevant essentially in everything we study in hydrostatics. So the problems are a little bit simpler, right? Now, if you recall Newton's second law, it can be written in its most general form as mass times acceleration equals sum of all the forces acting on an object. More generally, it can be written as the rate of change of momentum. So m is the mass of the object, and v in this expression here is the velocity, and v, as you know, can be a vector. So the rate of change of momentum equals sum of all the forces acting on the object, right? That's another way to look at Newton's second law, sort of a more general way of looking at Newton's second law, which is kind of handy when we study fluid dynamics. And the right-hand side can be made up of various forces, surface forces and body forces, right? And the surface forces are of two types. They could either be normal forces or tangential forces. We've introduced this in the earlier chapter, right? And hydrostatic problems, the fact that we don't have these tangential forces makes the study of hydrostatics problems that much simpler, right? So hydrostatic problems are thus fundamentally simpler than fluid dynamics problems. And the reason being, tangential forces are eliminated, and tangential forces only come in if these velocity gradients exist. And since those velocity gradients are not permitted, there's no tangential force in the problem of hydrostatics, right? So that's sort of the background, if you will. So now our goal is to derive sort of an equation, the fundamental equation for fluid statics. So we'll have an x, y, z, an inertial coordinate system as shown in this diagram. And let's imagine we have a large body of fluid that we're looking at. And let's take a piece of the fluid of length dx, dy, and dz as shown in this diagram, right? The x, y, and z correspond to the three coordinate directions. And let's imagine that the pressure force, and remember that the pressure force on a surface is always acting perpendicular to the surface in a direction towards the surface, right? So that's a notation, that's what we will use, right? So imagine a point at the center of this object of size dx, dy, dz, right? So to reach the right face of this object from the middle, I got to go a distance dy over 2 to reach the right face. And if the pressure at the center of the object is P, then to figure out the pressure on the right face, I take P and then I find the rate of change of pressure with respect to distance in the y direction, because I'm moving along the y direction, times the change in y, which is dy over 2. That gives me the pressure on the right face, and then multiplied that by the area gives me the force, which is shown by the arrow. Same idea on the left face. The only distinction is the left face is at a distance minus dy over 2, and so that's why this negative sign appears. Okay, so it's again a pressure on the left face multiplied by the area, and the reference point is at the center of this object dx dy dz. If I imagine the top, I can also imagine in general, I'm only going to focus on the x direction here. In general, I could also have a body force. I could have a body force per unit mass, which I label as Bf sub y. And then I need to multiply by the total mass of this object. And the total mass of this object can be obtained by taking the volume of the object, dx dy dz, volume of the fluid that is, multiplied by the density of the fluid, rho, right? So I then multiply this entire quantity mass, multiplied by the mass, the force per unit mass, the body force per unit mass. That gives me the body force in the y direction. Okay, so Bfy is the body force per unit mass along the y direction. Now I can apply Newton's second law to obtain the balance in the y direction, right? So I have surface forces and body forces in general, and Newton's second law really simplifies to some of the forces being equal to 0, because there's no acceleration in this case. And so if I look at all the forces acting in the positive y direction, so I have this force acting in the positive y direction on the left face. So that's shown by this expression over here. So it's the pressure on the left face multiplied by the area. And then on the right face, the force is acting in the negative y direction. That explains this negative sign. And then the third term over here is the mass times the mass times the body force per unit mass equals, in general, we could allow for acceleration. And so I've assumed that there's a mass, rho dx dy dz, and this entire block of fluid is accelerating to the right at an acceleration rate a sub y. Right? So this is F equals ma, except the ma portion, the ma portion of it does appear on the right hand side. On the left hand side is the net force F acting on this fluid object. Those two terms cancel out. Both of them are multiplying dx dy dz, one with a positive, one with a negative sign, and then the other terms combine, and then every term has a rho dx dy dz appearing in every term. So if I take all of that into account, and I'm copying this over to the next slide, after we cancel out the dx dy dz, what's left over in this equation is this negative dp dy comes about. That's right here. And then rho bf sub y comes about, and then on the right hand side I got rho a sub y comes about, right? So the term dx dy dz, which is the volume of this fluid element, drops out. So this is sort of the basic equation of hydrostatics. I'm just copying this over to the next slide, and I can similarly do Newton's second law in the x and z directions, and it's easy to see that wherever y appears, I would replace that by x. This y I would replace by x. This y I would replace by x if I want to apply Newton's second law in the x direction. Likewise, those three quantities that I just indicated, I can replace that by z in order to obtain Newton's second law in the z direction. So a compact expression that combines all of these results is this expression. It's minus gradient of p plus rho times the body force vector, that arrow doesn't appear very well, equals rho times the acceleration vector on the right hand side. And the gradient of p, if you go back to calculus, the gradient operator is simply I hat d dx plus j hat d dy plus k hat d dz. Operating on p is what we need to get the gradient of p. And del operator that I just wrote down is this quantity del. Right? That's a defining equation for the del operator. So I can interpret the hydrostatic equation in a multitude of ways. We'll consider what's called the swimming pool problem or the static atmosphere problem. And so the right hand side of equation 3 is 0, right? The swimming pool, the water is contained, there's no motion. And so the right hand side of there's no fluid acceleration. The right hand side is 0. And Bfx and Bfy are 0. There are no body forces in the x and y direction. There's only a body force in the z direction, in the vertical direction in the case of a swimming pool. And so equation 3 will simplify to the following equation. Right? So again, in a swimming pool, which this being the z direction, that's the water. right? There are no variations in pressure in the x direction or y direction or z direction. That's what the Newton's second law equation, the equation on the previous slide, reduces to. And the equation in the y direction is dp dy equals 0, and the equation in the z direction is this. Now, what these two equations tell us is P doesn't depend on x and doesn't depend on y. So if I take a horizontal plane, the pressure is the same in the entire horizontal plane. Okay, again, x, y, z, for your convenience, I've referred to over here. So in other words, since P is not a function of x or y, in general it's a function of x, y, and z, but in general here it is not a function of x and y, I can replace the third equation as the ordinary derivative dp dz is negative rho g, and as I mentioned in the first chapter in discussing fluid properties, this rho g will give it a new symbol. We'll call that gamma, the specific weight of the fluid. So in summary, we've looked at the hydrostatic equation for static fluid, and in this case, this equation applies only the relevant body force is gravity, and the assumption here is the z-axis is pointing upwards, right? The right-hand side will become plus gamma if the z-axis chosen is pointing